All right, hi everybody. This is a really quick last minute review for APPM 2360 exam 3. Um, I'm just going to toss a bunch of concepts that are relevant to exam 3 out. This video will likely be replaced by a higher quality production. So without further ado, let me share my screen. Let's get started. Oh my God, please work. Okay, nice. So let's get started. APPM 2360 exam 3 review. So let's get started talking about eigenvalues. Eigenvalues. And so eigenvalues, the relevant equation to determining eigenvalues is A times a vector, eigenvector V is equal to lambda times that same vector V, where V is a non-zero vector. So in order to find your eigenvalues, finding eigenvalues, you'll use the characteristic polynomial, so P of lambda, which is equal to the determinant of A minus lambda times the identity matrix I is equal to 0. If you solve this out, you can find your the values of lambda from each eigenvalue they determine. So for each eigenvector, or eigenvalue, which I'll denote as lambda sub I, we can find our eigenvectors, find eigenvectors via the equation A, or it should be blue. A minus lambda I times VI is equal to 0. So for each lambda I that you substitute in, you can find the associated eigenvector. And in this case, this matrix A, it needs to be in reduced row echelon form, so RREF, which means that it has at least one row of just zeros. Okay. So some properties that eigenvectors have, or eigenvalues have. So properties of eigenvalues. If I have, recall that the matrix A is actually encoding a linear transformation in this vector space V. So I'm taking it from I'm taking one vector, I'm transforming it into another with this matrix. If I have a matrix A to encode this transform, and I take its transpose, so if A, or not if, A and A transpose, they'll have the same characteristic polynomial because the determinant will be the same. So have same characteristic polynomial, so P of lambda, which means that consequently, they'll have the same eigenvalues. If I have the eigenvalue lambda for A, then 1 over A, or then I'll have, 1 over lambda for A inverse. And the final thing that I'll note is that the dimension of the eigenspace is equivalent to the number of linearly independent eigenvectors. And so I think this last part is probably best shown through an example. So let's say I have my eigenvector is 0, 1, 0. Then excuse me, then my eigenspace, I'll denote it with this double bar E, is equal to the span of that vector, 0, 1, 0. And the dimension of my eigenspace is equal to 1. All right, the next thing we're going to talk about is the Wronskian to test the linear independence of differential equation solutions. So Wronskian to test linear independence of differential equations solutions. Okay. So if I have my Wronskian of my system, so W of y1 all the way through yn, not equal to 0 at any point, then this is linearly independent. And just a bit of clarification about notation. What I've called y here, it's the same thing as f, f1, f2, so on. It's just representing the function that we're trying to solve. If my Wronskian is equal to 0 anywhere on some interval, so anywhere on the interval a, b, then that means that they are linearly dependent. Linearly dependent. Okay. So now you're pretty used to solving first and second order differential equations. Let's talk a little bit about higher order differential equations, and we'll touch more on this at the very end of the video. So now your goal is shifting from solving a first order or second order differential equation to solving n-dimensional, so solving n-dimensional homogeneous linear differential equation systems with constant coefficients. The way you're going to want to start this out is start by determining the characteristic equation first, and then factoring. Start by factoring characteristic equation. The dimension of your solution space is identical to the order of your differential equation. And once again, I think this is best illustrated with an example. I'll go to the next page for this. So let's say I have the system of differential equations, x1 prime, or x2 prime, and x3 prime. And these are equal to, respectively, 3x1 plus x2 minus x3, x1 plus 3x2 minus x3, and 3x1 plus 3x2 minus x3. From this, I can represent this as a matrix. So x vector is equal to the linear transformation, the matrix A applied to the x vector, which is just equal to the constants. So 3, 1, -1, 1, 3, -1, 3, 3, -1, applied to our vector x. So from this, I can find my characteristic equation. I'll determine my characteristic equation as follows. I'm not going to show the steps for determining each of these things. I'll give the solution directly. So characteristic equation will then be lambda cubed minus 5 lambda squared plus 8 lambda minus 4 is equal to 0, from which we can get our solutions for lambda. So lambda equals 1, which if we solve for our eigenvector associated with that, we'll get our v1 is equal to 113. Lambda, no, I'll call this lambda 1. Lambda 2 and lambda 3 are actually the same. So lambda 2 is equal to lambda 3, which is equal to 2. And that gives me my second eigenvector as 1, -1, 0. And I'll just determine my last eigenvector v3 to be 0, 1, 0. From this, I can bring out my solution. So x1 will be equal to e to the t times the first eigenvector, 1, 1, 3. X2 will be equal to e to the 2t. So e to the 2t, 1, -1, 0. And then x3 will also be e to the 2t because of this 2 associated with this associated to eigenvalue with this eigenvector. So e to the 2t times 1, 0, 1. And from this, I can form the entirety of my solution, which will be x of t, or vector x of t, will be a vector of x1 of t, x2 of t, x3 of t, which I can then just expand out as c1 e to the t times 1, 1, 3, plus c2 e to the t, 1, -1, 0, or e to the 2t, sorry, plus c3 e to the 2t, 1, 0, 1. And that's my final solution for this particular example problem. Okay, now let's talk a little bit about the method of undetermined coefficients. So undetermined coefficients. So finding particular, this is a method that you'll use when you want to find particular solutions. So y sub p to linear, homogeneous, or linear, non-homogeneous, constant coefficient differential equations. So what we're doing now is finding particular solutions to linear, non-homogeneous, constant coefficient differential equations. So the first and foremost thing that you're going to do, and the form that these differential equations take is L, where L is just some linear operator. L of y is equal to some function f of t. The first thing you're going to want to do is make your homogeneous solution. So make y sub h first. And this is just the homogeneous equation. It's something that you guys have seen a lot by now. It's just we're setting the right-hand side, so this forcing term equal to 0. After you have your homogeneous solution, you can form your particular solution. You're going to have to guess it and look it up in this table based on the nature of your forcing function. So if your guess, let me actually just outline the table real quick. So we've got, I'm not going to put in all of the forcing functions and associated particular solutions, but I'll just do a couple. So some example forcing functions could be, this is f of t, a constant k, some polynomial p of n, c times e to the kt, cosine omega t, or sine omega t. And then this one's a really long one, but Pn of t times cosine of omega t plus Pn of t times sine of omega t. Okay, and so the associated particular solutions for each of these are going to be respectively a sub n, and I'm not going to expand this out. You guys should you guys can probably recall this from class. This would be a times e to the kt. This would be a cosine omega naught t plus b sine of omega naught t. This would be a sub n cosine of omega naught t plus b sub n sine of omega naught t. But these are just like coefficient polynomials. If you run into a situation where, so if your guess, if your initial guess ends up being part of the basis of your homogeneous equation, then you can just keep multiplying it by t until it works out. So if your guess ends up being within the span or in the basis of your homogeneous solution, multiply by t until no longer so. Okay, sick. Let's move on to the harmonic oscillator. So the harmonic oscillator. So actually, first and foremost, let's draw a diagram of what the harmonic oscillator looks like. So you're going to have, if we have a horizontal harmonic oscillator, it'll probably look something a little bit like this, where this is a wall, that's a floor, and we have a spring attached to that wall that's holding a block of mass m. The initial position of this, the equilibrium position at rest, is x equals 0, and the left side will have x less than 0. The right side will have x greater than 0. If we have a vertical system, this one, it's a little tricky to just remember the coordinate system. So if you pay attention to anything in this video, I'd pay attention to this. I have the same wall, I have a spring attached with a mass m, and here my equilibrium position is the same as before. It's the center of the block, so this is x equals 0. X equals 0. But this side is negative x, and this side is positive x. That was just something that confused me a lot. Cool. Let's discuss the actual equation. So the harmonic oscillator is defined by the equation mx double dot plus bx dot plus kx is equal to your forcing function f of t. Here, m is your mass, which will be greater than 0 and likely have units of kilograms, for instance. B is your damping factor, which is greater than or equal to 0, and it will have units of newtons per meter per second or newtons times second per meter. And this makes sense because you can think about it as how much force is going to be restoring this damping how much force will be damping it as it moves. So the faster it's moving, the more damping I'll have to have. If, like, for instance, you try pushing a dash pot or you're trying to close an automatic door and it's pushing back against you, that's an example of damping. So the faster you push it, the more resistance you're going to get. That's why these units, you end up getting units of something like newtons times second per meter. The constant K is your restoring constant, and it has units of newtons per meter. And you probably remember that from Hooke's law. And then f of t is your forcing function. Just a quick note that if b is equal to 0, this is called undamped. And if f is equal to 0, then this is called unforced. And so this k value is usually something that we have to determine. So how do we get k? How do we get k? So usually you'll be given some sort of information in the problem statement that some force, so a force in newtons is required, so some quantity of force F in newtons is required to push or pull your mass by a displacement x, which is in meters, then you can determine k as being F over x. Let's just quickly clarify the initial conditions. I should have done this earlier. The initial conditions of the simple harmonic oscillator. So x at times 0 is equal to x naught, which is your initial displacement from equilibrium. X prime or x dot of 0, which is equal to your initial velocity. Cool. Let's talk a little bit more about this scenario here, undamped and unforced. So undamped and unforced. In this case, our equation will be simplified to mx double dot plus kx is equal to 0. And solutions to this will take the form of x of t. Excuse me. X of t is equal to c1 times cosine of omega naught t plus c2 times sine of omega naught t. And here this omega naught is a quantity that we call the circular frequency. So omega naught is equal to the square root of k over m. A thing you should know about actually, we'll talk about that later. You can also convert this from Cartesian coordinates to polar coordinates. So the polar form will take of the solution will be x of t is equal to a times cosine of omega naught t minus delta, where a is equal to c1 squared plus c2 squared, and tangent of delta is equal to c2 over c1. And then you can convert between finding a and finding delta and determining c1 and c2, because c1, you can just invert this, is equal to a cosine of delta, and c2 is equal to a times sine of delta. And so if you take a look at your simpler harmonic oscillator system in this phase space where our y-axis is defined by x dot and our x-axis is defined as x, an undamped, unforced oscillating system will just continue to loop around and around on the same track in phase space. There's no loss of energy to anything. And so let's also just quickly describe the periodic analogs to the harmonic oscillator system. So periodic properties. We have a natural frequency. So the natural frequency, which we denote as F naught, is equal to omega naught over 2 pi. And we can use that to get our period. So our period T is equal to 1 over F naught. Cool. Let's quickly talk about solutions to second order differential equations with constant coefficients. Let me move this up a little bit. So solutions to second order differential equations with constant coefficients. Sorry, my handwriting is getting progressively worse. Here's examples of systems that are second order differential equations with constant coefficients. We have A times y double prime plus B times y prime plus C y is equal to 0. And mx double dot plus bx dot plus kx is equal to 0. So that's just a simple harmonic oscillator. Okay, so from this we can determine our characteristic equation, which is defined as AR squared plus BR plus C is equal to 0. And from this we can also get our determinant, or I don't know if determinant is the right term, but delta is equal to B squared minus 4AC. There's 3 cases that you want to consider. You have the case where delta is positive. Let me also move this up a little bit more. So delta is positive, delta is equal to 0, and delta is negative. In each of these cases, you will have 2 associated roots, but one of them may be a repeat of the other. So if my delta is positive, R1 and R2 are defined as negative B over 2A plus or minus B squared minus 4AC over 2A. If delta is equal to 0, then I'll have one repeated root. R is equal to negative B over 2A, and the other root is also just negative B over 2A. If my delta is negative, then I will have R1 and R2 defined as alpha plus beta I, as defined in class. So let's talk about how we convert from this to our homogeneous solution. Note that this is a homogeneous differential equation. We have a 0. We have a 0 on the right-hand side, so there's no forcing term. So the homogeneous solution for this first case is going to be C1 e to the R1t plus C2 e to the R2t. For the second case, where the determinant is 0, y sub h is equal to C1 e to the RT plus C2 e to the RT, where or C2 times t e to the RT. That's the difference because we have that repeated root. Y sub h for this third case, where the determinant is negative, is e to the alpha t C1 times cosine of beta t plus C2 of sine of beta t. Okay. Okay. And so we can produce associated graphs with each of these types of the determinant. So let me just draw 3 axes real quick. So if it's overdamped when the determinant is greater than 0, it'll look something a little like this. If it's critically damped, when the determinant is equal to 0, it'll look a little like that. And then underdamped, it'll oscillate, but also like die out as it goes over time. So also note that for these two, it must cross the axis at most once. Cross axis at most once. Okay, let's move on to talking about variation of parameters. Variation of parameters. Okay, so what you're going to want to do here is find y sub h first, your homogeneous solution first, which will help form the basis of yp. So then you'll make basis of y sub p, your particular solution. You'll get as y1 and y2. You may need to reformat the differential equation because you need the leading coefficient to be 1. So reformat dE so that leading coefficient is 1. So then my particular solution turns out to be v1 y1 plus v2 y2. And then we know that v1 prime is equal to negative y2 f over omega, or w, sorry, it's w. v2 prime is equal to y1 f over w. And because this is a pretty conceptual topic, I think it's best to illustrate this with an example. So our example will be, we're going to try and solve the differential equation y double prime minus 2y prime plus y is equal to e to the t over 1 plus t squared. We're going to use this example because it has an unusual forcing function. Unusual forcing function. Okay. So my homogeneous solution, y sub h, I will find first the characteristic equation. So that'll be r squared minus 2r plus 1. I just got that from here. And that'll be equal to 0. From this, I get my solutions that r is equal to 1. And that is the only solution. So I have this repeated solution, which means that my basis will then be e to the t and t times e to the t, because I'm just multiplying it by t because I have this repeated root. We'll call this one y1. We'll call this one y2. So now let's take the Wronskian of y1, y2. That's equal to the determinant of this matrix, e to the t times e to the t. If we take the derivatives, that'll be e to the t. This will be t plus 1 e to the t. And we take this determinant, we get t plus 1 e to the 2t minus t times e to the 2t, which is just equal to e to the 2t. We can now take these defined derivatives that v1 prime is equal to negative y2 f over w, and v2 prime is equal to y1 f over w. Let's substitute in the values that we got from our original differential equation. So this is negative t over 1 plus t squared. This will be 1 over 1 plus t squared. And then to find the actual v1 and v2, we can integrate. So v1 is equal to integral of this, negative t over 1 plus t squared dt. v2 is equal to the integral of 1 over 1 plus t squared dt, which is just equal to this bottom one, it'll just be arctangent of t. This top one, we're going to have to pull a little sneaky trick. We'll multiply it by negative 1/2 on the outside, put 2t on top, 1 plus t squared. This is just an integrating trick we have to pull. And that means that our final integrand is negative 1/2 natural log of 1 plus t squared. From this, I can now form my particular solution, yp is equal to v1 y1 plus v2 y2, which is equal to negative 1/2 e to the t natural log 1 plus t squared plus t e to the t arctangent of t. That means that our general solution, so general solution, we get this y as by adding up our homogeneous and our particular solutions, which gives us the final expression e to the t c1 plus c2t minus 1/2 natural log of 1 plus t squared plus t arctangent plus t arctangent of t. That's our final answer. Okay, let's very quickly talk about Euler-Couchy. I'm not sure if this was covered in class this year or not, but we'll just quickly discuss it. Euler-Couchy. It may have come up on a homework. So for Euler-Couchy solutions, we'll let y is equal to t of r, and that'll be our characteristic equation. And then if my determinant, delta is less than 0, then r is equal to alpha plus beta I. And so this is to solve equations of the form a t squared y double prime plus b t y prime plus c y is equal to 0. Using Euler-Couchy, we end up getting, if you follow this methodology out, you'll get a solution that y of t is equal to t to the alpha times c1 cosine beta natural log of t plus c2 sine of beta natural log of t. Cool. Now let's talk about forced oscillations. So forced oscillations. If I have my harmonic oscillator, so mx double dot plus bx dot plus kx is equal to this periodic forcing f naught times cosine omega f, but that's the frequency of my forcing, times t. Then we'll end up with two scenarios. We'll end up with an undamped. We could either end up with an undamped system, or we can end up with a damped system.
Yes.
In undamped systems, there's two forms that you'll see. You could find beats, and this is if your omega naught, the characteristic frequency, is approximately the same as your forcing frequency, or you can get resonance, where your characteristic frequency is equal to your forcing frequency. And this is what they talk about in every engineering class with like the Tacoma Narrows Bridge and how it collapsed because people were walking on it. They were forcing it at the same rate of the natural frequency of the bridge. So let me just draw the two graphs. If you have beats, it'll look a little something like this. We just have an oscillatory motion that's repeated. If you have resonance, you're going to see that your response, actually, let me draw this a different way. Your response is going to grow in a bounded manner. So you'll have something that looks a little like that. If your system is damped, and that means that your determinant, so b squared minus 4mk, it could be 0, which means that it's overdamped. It could be equal to 0, which is critically damped, crit damped, or it could be negative, less than 0, which means that it's underdamped. If you have an underdamped system, then you'll have a transient part of your solution as t goes to 0, since alpha is less than 0. So we'll have our final solution x of t, which is equal to our homogeneous solution x of h plus x of p. This will be our steady state term. This will be our steady state solution. And this will be our transient term, which will decay as t goes to 0, or t goes from 0, since alpha is less than 0. Okay, perfect. Last thing we're going to talk about is converting higher order differential equations to systems. So converting higher order differential equations to systems of equations. So the important thing to note here is that the coefficient of your highest order derivatives, so yn, must be 1. If it isn't, then you have to rearrange your differential equation until it is 1. I think this is best illustrated with an example. So let's solve the differential equation or let's represent this differential equation as a system. So y triple prime plus 3y double prime plus 5y prime is 2y is equal to e to the negative t. And I'll give you the initial conditions that y of 0 is 1, y prime of 0 is 3, y double prime of 0 is 2. Okay, so let me set x1 equal to y. I'll set x2 equal to y prime, and I'll set x3 equal to y double prime. I'll take this and I'll differentiate with respect to t. So now I have a system x1 prime, which is just y1, that's just x2. Or sorry, that should be y prime. X2 prime is equal to y double prime, which is just x3. And x3 prime is equal to y triple prime, which we can solve out from this differential equation. We'll just bring all this over to the other side. And we do that and we get negative 3y double prime minus 5y prime minus 2y plus e to the negative t, which if we substitute in what we know y prime and y double prime to be, we'll get 2x1 minus 5x2 minus 3x3 plus e to the negative t. Now that I have this, I can just represent this as a system of equations. So x1 prime, x2 prime, x3 prime. This vector, which I'll call x prime vector, this is equal to my coefficients matrix 0, 1, 0. Looking at this, 0, 1, 0, 0, 0, 1, -2, -5, -3. And I'm just taking the coefficients from these equations here. That times my vectors x1, x2, x3, sorry, my variables, plus 0, 0, e to the -t. With the initial condition that x of 0 is equal to 1, 3, 2. This is my constants coefficient A, or my coefficients matrix A. This is my vector x, and this is my forcing term f. Cool. That's it for today. Best luck on the exam.